This is the first of 3 presentations on very widely used probability density functions. And so we're going to talk about the uniform probability distribution, which is probably the simplest probability density function of all of them, because it is nothing but the following. A continuous random variable is said to have a uniform distribution on an interval AB if and only if its probability density function is f of x and then parameters a and b is 1 over b minus a for a smaller or equal x smaller or equal b and 0 otherwise. Well, that's kind of hard to read. Basically, what the uniform distribution does is it assigns 0 probability to anything outside the interval AB, and it basically, as much as this is possible in a continuum, it assigns the same probability to every outcome inside the interval. And in order to make sure, so that already means that the function, of course, is greater or equal than 0. And to make sure that the total area of this rectangle then is 1, of course, we must have that the height of this rectangle is 1 over b minus a. And so now if you look at this picture and you go back to the symbolic definition, you see that's exactly what the symbolic definition does. It gives us 0 outside the interval AB, and it gives us 1 over b minus a inside the interval. And I really didn't mark here with dots that these 2 points are at height 1 over b minus a, because as we have seen for continuous distributions, whether these inequalities are strict or not really doesn't matter. The probabilities don't change. Alright, now with a probability density function that is this simple, basically our interpretation of probability as area already is good enough to compute probabilities, and we don't really need calculus to integrate constant functions. And so we're going to just talk about rectangles here as we now solve a bunch of problems. Before we get there, however, let's also ascertain that even though this is a very convenient density, it is a real density. It has real examples, namely the function rand, the spreadsheet function rand that I often referred to or have referred to previously, that actually is uniformly distributed on the interval from 0 to 1. So basically, if I take a spreadsheet and type in rand, this function that has no argument, here I got a value of 0.30178, and now this spreadsheet is set up in such a way that every time something is changing, every time something is edited, it recomputes all the cells. So if I recompute rand, I get 0.91 something, I get 0.97 something, I get 0.21 something, I get 0.45 something, and so on, and so on, and so on. And so now if I were to collect these measurements, of course, that's sort of like collecting outcomes of coin flips, but in a spreadsheet, I could just go ahead and query this random variable something like 200 times and set up a histogram. Then basically that histogram is going to sort of look like, or will give us bars between 0 and 1, where 0 is here, 1 is here, and all the bars ought to be roughly the same height. They're not going to be exactly uniform all the way across. There will be some fluctuations, but basically the experimental outcome will look very much like a uniform distribution. So that means this thing is implemented through random number generators and the like. And well, so now let's take a look at some examples, and these examples are just designed to drive home the point that probability is area. So we're going to look at one random variable x that is uniformly distributed on an interval from 2 to 5, and we're going to compute each of the following probabilities. The probability that x is less than or equal than 3. Well, 3 minus 2 is 1, divided by 3 is 3, right? And if we really want to make sure of this stuff, we just go ahead and draw the distribution. We realize that 3 is here, so the probability that x is less than or equal than 3 is the probability that x is between 2 and 3. It's exactly this area of this rectangle, and that is the height 1/3 times 1, which is just 1/3. Okay, so let's keep going with that. And if we want to have the probability that x is greater or equal than 4, well, similar situation. We look at the probability density. 4 is here, which means that this rectangle here is the area that represents the probability. Remember, the height is 1/3, and so the probability of x greater or equal than 4 is the probability that x is between 4 and 5, and that is still 1/3 because the height here is 1/3. If we're looking at the probability that x is between 3.5 and 7, well, then we have to be a bit careful because, well, 3.5 is here, and 7 is somewhere over here where already the probability distribution assigned, the probability density already assigns 0 probability. So actually, the probability is completely captured in this rectangle, which means that for this random variable, the probability that x is between 3.5 and 7 is the probability that x is between 3.5 and 5, because the probability that x is greater than 5 is 0, and that ends up being, well, 1.5 times 1/3, and that's 1/2 because it's exactly half the area of the whole thing. Yeah, I didn't put the steps in there. Okay, so now let's keep looking at the random variable that is distributed uniformly between 2 and 5, and let's look at a different problem. Let's look at the problem of computing a value x so that the probability that our random variable is greater or equal than x is 0.7. That's the kind of scenario that, even though the probability density functions will be different and may have to even be found empirically, that's the kind of thing that you can face in design, that you want to build something in such a way that you've got a 70%, a 90%, a 99% chance that something is going to happen within, is or isn't going to happen within a certain time. That's where a lot of these abstract computations come in. And well, still, you just have to look at your underlying density function. And this time we want an area to the right of a point x, and that area is supposed to be 0.7, right? So we put a point x here, and we want to have that this total area here is supposed to be 0.7. Well, that means that this area here is 0.3, and so that means 1/3 times the step to the right from 2 has to be equal to 0.3, so 1/3 times delta equals 0.3, that ought to be 0.9, so this ought to be 2.9. Well, alright, let's see what the computation gives us. X is here, and so basically what I have is 0.7 divided by 1/3, that is this length, that works out too. So that's 0.7 times 3, that's 2.1, and then x is 5 minus 2.1, and that would be 2.9. So I've worked with the left side, which is basically then the complementary event if we want to use the language that we have also introduced, and either way I get the right result here, and well, you will too. There's nothing special about me. I mean, these computations aren't that hard. Okay, so what am I looking for? I'm looking for a way to look at you. Yeah, okay, so these computations aren't that bad. What we're trying to drive home with the uniform distribution certainly is this idea of probability being area, and also of the value of drawing these pictures. Drawing the pictures isn't mandatory to solve these problems, even for more complicated distributions, but I found that it helps visualize things, and it also helps visualize situations where we may have to go to the complementary event, which at the latest can happen when we're working with the normal distribution, which is actually computationally rather complicated. But before we get there, the next one that I've actually planned for you is the exponential distribution, so I'll see you there.